The density of a substance is its mass per unit volume. That is, it is the ratio between its mass and its volume. And here is the expression for the density of a substance. Now, if you move volume to the left hand side and density to the right hand side, then the volume of a substance is given by the ratio between its mass and its density. Now let us divide both sides by 1 mole. Then on the left hand side, we have volume of the substance per 1 mole of the substance. And on the right hand side, we have mass of the substance over 1 mole of the substance multiplied with its density. And mass of the substance per 1 mole of the substance is nothing but its molar mass. So let us replace this ratio with molar mass. And molar mass is denoted by capital M. Then on the right hand side, we have a ratio between the molar mass of the substance and its density. On the left hand side, we have the volume of the substance per 1 mole of the substance. If mass of the substance per 1 mole of the substance is called molar mass, then volume of the substance per 1 mole of the substance will be called molar volume, right? And that's exactly what we have here. So molar volume is the volume of the substance per 1 mole of the substance, and it is given by the ratio between its molar mass and density. Molar volume is denoted by capital V with the subscript small m. Now what are the units of molar volume? If volume is expressed in liters, we have capital L in the numerator, and in the denominator we have the unit mole. So molar volume has the unit liter per mole. See, this is no rocket science. If the volume of a substance is its mass over its density, then molar volume is its molar mass over its density. As simple as that. Now let us work out some examples. If the density of pure water at this temperature and pressure is this, then what is its molar volume? Molar volume is the ratio between its molar mass and its density. What is the molar mass of water? You should know the molecular formulae of some familiar compounds like water. And from the molecular formula, by now, you should know how to calculate its molar mass. We have done a lot of examples in the previous videos. The molar mass of water is 18.0 gram per mole. And the density of water at this temperature and pressure is given as 1.0 gram per milliliter. But let us convert this volume into liters. It will be 1.0 gram per, 1 milli is equal to 10 to the power of minus 3. So it would be 10 to the power of minus 3 liters. So it would be 1.0 times 10 to the power of 3 gram per liter. Now simply put these values in this expression to get its molar volume at this temperature and pressure. It would be 18.0 gram per mole over 1.0 gram, 1.0 times 10 to the power of 3 gram per liter. Now cancel these two units and simplify this to get its molar volume in liter per mole at this temperature and pressure. Now don't think that you have to use every piece of information that is provided in the question. To answer this question, we did not use the temperature and pressure mentioned in this question. We don't need these values to answer this question, right? Now, in this question, we are given the density of helium at this temperature and pressure. We are asked to find its molar volume at this temperature and pressure. Again, molar volume is given by the ratio between its molar mass and its density. Now, what is the molar mass of helium? The atomic weight of helium is approximately 4. So, the molar mass of helium would be 4.0 gram per mole. And the density of helium is given as 0.1785 gram per liter at this temperature and pressure. Then you simply have to substitute these values here to get its molar volume. In this example, we have calculated the molar volume of water, that is a liquid at this temperature and pressure. Here we did the same for helium, that is a gas at this temperature and pressure. So you can calculate molar volume for any substance, solid, liquid, or a gas. Now, whenever we think of the volume of a gas, a very simple yet powerful law comes to our mind. That is Avogadro's law, previously known as Avogadro's hypothesis. And it states that equal volumes of all gases contain equal number of molecules when measured at the same temperature and pressure. Remember, Avogadro's law is applicable only to gases, not to solids and liquids. And as it states, if you take equal volumes of various gases at the same temperature and pressure, then they would all have the same number of molecules. Now, can we reverse this statement? That is, can we say if we take gases containing equal number of molecules, then do they have equal volume when measured at the same temperature and pressure? Yes. If this statement is true, then the converse must also be true in this case. So that means if you take X number of molecules of helium, X number of molecules of hydrogen, and the same number of oxygen molecules, same number of carbon dioxide molecules, and so on, because all these gases have the same number of molecules, they must all have the same volume when measured at the same temperature and pressure. That is what this statement says. Now, let us take 1 mole of each of these gases. And you know that 1 mole of any substance, whether it is a solid or a liquid or a gas, contains an Avogadro's number of particles. So if you take 1 mole of different gases, they also contain the same number of molecules. Each of these gases has an Avogadro's number of particles. Because they all have the same number of particles, they must all have the same volume when measured at the same temperature and pressure, right? That is what this statement says. If the number of molecules are same, then their volumes must be same when measured at the same temperature and pressure. And we have a special name for the volume of any substance per 1 mole of that substance, that is molar volume, right? So whatever we have here is the volume per 1 mole of the substance. That means it is molar volume. So what we understood here is the molar volumes of all gases is the same when measured at the same temperature and pressure, because they have the same number of molecules. So remember, the molar volume of all gases is the same when measured at the same temperature and pressure, because they all contain the same number of molecules. Now, a very interesting point in this discussion is, in case of gases and only gases, the volume at a given temperature and pressure depends only on the number of particles or molecules present in it and nothing else. See here, helium is monoatomic. That is, a molecule and an atom are one and the same in case of helium. These two are diatomic, and in a carbon dioxide molecule there are 3 atoms, and if you take a methane molecule there are 5 atoms in each molecule. Yet they would all have the same volume if they all contain the same number of molecules. A helium atom is much lighter than a carbon dioxide molecule. Doesn't matter. If you have equal number of them, then they would have the same volume. So the volume does not depend on the number of atoms present in each of these molecules, the mass of the molecule, the chemical composition of the molecule. Here, a molecule of carbon dioxide is composed of carbon and oxygen atoms, whereas this is composed of carbon and hydrogen atoms, whereas these are elements. No, it doesn't matter. If you have equal number of molecules, they would all have the same volume at the same temperature and pressure, and this is quite interesting, right? Now let us get back to our molar volume. Molar volume is the volume per 1 mole of the substance, and 1 mole of any substance contains an Avogadro's number of particles. So if you take 1 mole of different gases, they all contain the same number of molecules, and if they all have the same number of molecules, they all must have the same volume when measured at the same temperature and pressure, according to Avogadro's law. Remember, this is true only in case of gases. It may not be true in case of solids and liquids. That is because Avogadro's hypothesis or law is applicable only to gases, not to liquids and solids. So, molar volumes of all gases are the same when measured at the same temperature and pressure. That means 1 mole of all gases have the same volume when measured at the same temperature and pressure. Because the volume of a gas is sensitive to temperature and pressure, that means it changes significantly with a change in temperature and pressure. Whenever you compare volumes obtained from different experiments, you have to compare them at the same temperature and pressure. Otherwise, that comparison does not make sense, right? So we need a standard and IUPAC created a standard called Standard Temperature and Pressure, and it has the abbreviation STP. STP stands for Standard Temperature and Pressure. And in this standard, 0 degrees centigrade or 273.15 Kelvin is taken as the standard temperature, and 100 kilopascals or 1 bar is taken as the standard pressure. And there is another standard that is in use for a very long time, that is called normal temperature and pressure, and this has the abbreviation NTP. And in this standard, the standard temperature is 20 degrees centigrade or 293.15 Kelvin, and the standard pressure is 1 atmosphere or so many pascals. Now, we can calculate the molar volume of any gas by using what is known as universal gas constant or molar universal gas constant, that is denoted by the letter capital R. We can calculate the molar volume of any gas at any temperature and pressure by using this universal gas constant. And if you calculate the molar volume of a gas at STP, it will come to be 22.71 liter per mole. And if you do the same calculation for NTP, it comes to be 22.4 liter per mole. That means 1 mole of any gas at STP occupies a volume of 22.71 liters, and 1 mole of any gas at NTP occupies a volume of 22.4 liters. Now, we expect all gases to show some properties. We shall discuss what these properties are later in this series, but understand that we have some expectations of gases. Now, all the gases that we know of, like hydrogen, helium, nitrogen, oxygen, carbon dioxide, etc., are known as real gases because they are real. They exist. Either they exist in the nature or they can be prepared in a laboratory. But all these real gases fall short of our expectations. They do not meet our expectations. Then, where do I find a gas that meets or satisfies all my expectations? You cannot find such a gas in reality. You can only imagine such a gas. Such an imaginary gas that meets all our expectations is called an ideal gas or a perfect gas. And no real gas is an ideal gas because all real gases fall short of our expectations. Therefore, ideal gas or perfect gas is only an imaginary gas. It does not exist. But for our academic purposes, though real gases are not ideal gases, we treat them as if they are ideal gases unless otherwise specified. So, understand that real gases are not perfect gases, ideal gases, but we treat them as if they are ideal gases for our academic purposes unless mentioned otherwise. So kindly bear this in mind. And with that, we are ready to work out some problems again. This question says a sample of ethane, which is a colorless, odorless gas, has so much volume at STP, and we are asked to calculate the amount of substance or the number of moles and the number of molecules present in that sample of gas and the mass of the sample. Now, how do we answer this question? Now, we know one fact, that is the molar volume of an ideal gas at STP is 22.7 liter per mole. That means 1 mole of an ideal gas at STP has 22.7 liters volume. And with that, we are ready to work out some examples again. In this question, we are asked to calculate the volume of so many moles of helium at STP. Now, how do we answer this question? We know that the molar volume of a substance is its volume per 1 mole of that substance. And for an ideal gas at STP, the molar volume is 22.7 liter per mole. That is, 1 mole of an ideal gas at STP occupies a volume of 22.7 liters. Then, what will be the volume of 1.1 moles of an ideal gas at STP? To get that, you have to simply multiply the amount of substance with the molar volume, right? Molar volume is the volume per 1 mole, and if you have an amount of substance equal to N, to get the total volume, you have to multiply its molar volume with the amount of substance. Now, what is the amount of substance given here? 1.1 mole. And what is the molar volume of an ideal gas at STP? This much. Remember, we treat all real gases as ideal gases, right? So just you have to make sure that the substance we are talking about is a gas at STP. If it is a gas, though it is a real gas, we treat it as an ideal gas. So take its molar volume at STP as 22.7 liter per mole. And these two get cancelled, and simplify this to get the volume of this sample of helium at STP in liters. Now, in the next question, we are asked to calculate the volume of 8.0 grams of oxygen at STP. If you know the molar volume of any substance, you can get its volume by multiplying its molar volume with the amount of substance, right? That's what we have done here. For an ideal gas at STP, the molar volume is 22.7 liter per mole. You must know this. So, to get the volume of this sample at STP, you have to multiply 22.7 liter per mole with the amount of substance. Remember, we treat oxygen as an ideal gas. But here we do not have the amount of substance. We are given the mass of oxygen. How do you calculate the amount of substance? You have to divide the given mass with its molar mass, right? And at STP, oxygen is composed of oxygen molecules, so its molar mass is 32.0 gram per mole. So this is the amount of substance, and if you don't want to use this unit, call it number of moles. So put this value here. It would be 8.0 over 32.0, and mole inverse in the denominator comes to the numerator and becomes mole, right? So these two get cancelled, and simplify this to get the volume of this sample of gas, oxygen, at STP in liters. Now what do we have in the next question? Calculate the mass of a sample of methane that has a volume of 5.6 liters at STP. I think this is the opposite of this question. Here we are given the mass and asked to calculate the volume, but here we are given the volume and asked to calculate the mass. How do you do that? Now, to know the mass of a sample, if you know the amount of substance, you have to multiply the amount of substance with its molar mass, right? Because amount of substance is the ratio between these two. So to get the mass of the substance, you have to multiply amount of substance with its molar mass. But here we are not given the amount of substance. Instead, we are given the volume of the gas at STP. Now first make sure that the substance we are talking about is a gas under these conditions. Yes, methane is a gas at STP. So to know the mass, we have to know the amount of substance and molar mass. We can figure out the molar mass from its molecular formula. Molecular formula of methane is CH4. You must know this, and its molecular mass would be 16.0 gram per mole. By now, you should know how to figure this out. And if you know the amount of substance, then we know its mass, but we don't have it in the question. So you have to figure this out. But we are given the volume of the gas at STP. Now you also know the molar volume of any gas at STP. It is actually 22.7 liter per mole, but because the number we are given here is 5.6 liters, let us use 22.4 liter per mole, because 4 times 5.6 is 22.4. This looks funny, but I think that's how we have to approach this question. And how do you get the amount of substance? See here, to get the amount of substance, you have to divide the volume of the sample with its molar volume. So it would be V over Vm. That is 5.6 liters over 22.4 liter per mole. So you would get the amount of substance in mole and put that here. So it would be 5.6 over 22.4 mole times 16.0 gram per mole. Cancel these two and simplify this to get the mass of the substance in grams. See, you don't have to memorize any formula here. In the next question, we are asked to calculate the number of molecules present in a given volume of carbon dioxide at STP. You know that Avogadro's constant gives the number of particles present per 1 mole of the substance. And if you multiply that with the amount of substance or the number of moles, if you don't care about the unit mole, then you would get the total number of particles present in that sample. So the number of particles, and in this case molecules, because carbon dioxide is composed of molecules, is given by amount of substance multiplied with Avogadro's constant. We know the value of Avogadro's constant. It is 6.022 into 10 to the power of 23 per mole. But we are not given the amount of substance in the question. Instead, we are given the volume of the gas at STP. So from this information, you have to figure out the amount of substance. How do you do that? You can do that using the molar volume of a gas at STP. You know that the molar volume of an ideal gas at STP is 22.7 liter per mole, but by looking at this number, they are expecting you to take its volume as 22.4 liter per mole. So to get the total volume of the sample, you have to multiply the amount of substance with its molar volume. Molar volume is per mole, and if you multiply with the amount of substance or the number of moles, if you don't care about the unit, you would get the total volume. Then the amount of substance is given by the ratio between the volume of the sample and its molar volume. Now, what is the volume of the sample? 2.8 milliliters, but molar volume is in liters, so you have to convert this into milliliters. So 2.8 times 10 to the power of minus 3 liters over 22.4 liter per mole. Now simplify this to get the amount of substance in mole and substitute this value here and multiply it with Avogadro's constant to get the number of molecules. Now the next question is very interesting. We are asked to calculate the volume occupied by so many moles of helium and so many moles of carbon dioxide at STP. First, you have to make sure that these two are gases at STP, and of course they are both gases at STP. You must know that. Secondly, understand that there is no chemical reaction between helium and carbon dioxide. So they are non-reacting gases. Then how do we figure out the volume of this mixture? Remember, the volume of a gas at a given temperature and pressure depends only on the total number of particles or molecules, right? It does not depend on the mass of the particles, the chemical composition of the particles, and nothing else. It depends only on the total number of particles. So it doesn't matter if this mixture is composed of molecules of only one type or it is composed of molecules of different types. As long as the number of molecules are the same, the volume must be the same at the same temperature and pressure. That is Avogadro's law, right? So the volume of this mixture depends then only on the total number of molecules or the total number of moles, right? So it doesn't matter if the gas is a mixture of two or more non-reacting gases or it is composed of a single gas. So treat this mixture as a single gas to figure out its volume then, right? So total how many moles are there, or what is the amount of substance we have? 0.5 mole plus 0.75 mole, right? Multiplied with the molar volume of an ideal gas at STP, and that is 22.4 or 7. I will let you figure that out. I am using this one. Okay, so simplify this to get the volume of this mixture in liters. In the next question, we have a sample of ethane, which is a colorless, odorless gas that has a volume of so many liters at STP, and we are asked to calculate these three. I think you can try this for yourself. We have done similar examples above. But you must know the molecular formula of ethane is C2H6. What do we have next? What would be the volume of the following at STP? To get the volume of a substance, you have to multiply the amount of substance with its molar volume. Here we are talking about ozone, and it is a gas at STP, and we treat it as an ideal gas. So the molar volume of an ideal gas at STP is 22.7 or 22.4 liter per mole, depending upon the textbook you are following. Then the number of moles given the mass of the substance is, you have to divide the given mass with its molar mass, and the molecular formula of ozone is O3, so its molar mass is so many gram per mole. Put these values here to get the volume in liters. 3.011 times 10 to the power of, say, 22 atoms of helium. Again, to get the volume, you have to multiply the amount of substance with its molar volume. But here we have the number of atoms. To get the amount of substance given the number of atoms, you have to divide it with Avogadro's constant per mole, and it comes into the numerator. So, and you know the molar volume is the same. We treat all of them as ideal gases. Then what about so many kilomoles of sulfur dioxide? Simple. Here the number of moles are directly given, so multiply it with molar volume. Again, 8 grams of hydrogen would be 8 grams over 2.0 gram per mole. This is the amount of substance. Remember, hydrogen is composed of hydrogen molecules at STP, so you have to take the relative molecular mass in gram per mole, and hydrogen is a diatomic gas. So that is about that question. Then calculate the number of molecules present in a gas that has so much volume at STP. I think you can give it a try. Now, which of the following statements are true? We have 1 mole of ethyl alcohol and 1 mole of hydrogen peroxide at the same temperature and pressure. Will they have the same volume? We have equal number of moles, or the amount of substance is same, so we have equal number of molecules and they are at the same temperature and pressure. Then they must have the same volume, right? But remember, this equal number of molecules having equal volume at a given temperature and pressure is applicable only to gases, not to liquids and solids. But at this temperature and pressure, ethyl alcohol and hydrogen peroxide are not gases. So this equal number of molecules having equal volume logic is not applicable to gases. So this may not be true. I cannot tell. Then we have equal masses of oxygen and helium. Will they have the same volume at STP? See, both of them are gases. We treat all gases as ideal gases, so we are good. And they are both at the same temperature and pressure. They would have the same volume at a given temperature and pressure if they have the same number of particles. So you have to figure out the number of molecules present in these samples. How do you do that? You have to divide the given mass with the relative molecular mass of the substance in grams, right? So it is 32 for oxygen. At this temperature and pressure, oxygen gas is composed of oxygen molecules. So this is the number of moles of oxygen, and the number of moles of helium is 1 gram over 4.0 gram, and obviously these two are not equal. So the number of moles are not equal, so the number of molecules are not equal, so they will not have the same volume though they are at the same temperature and pressure. Molar volume of any substance at STP is this much. No, this is obviously false. When you say any substance, it could be a solid or a liquid or a gas. But 22.7 liter per mole is the volume of an ideal gas at STP. So this number is not applicable to solids and liquids. So this is false as well. What do we have next? To have equal number of molecules, take equal volumes of sugar and water at room temperature and pressure. See, equal volumes having equal number of molecules logic at any given temperature and pressure is applicable only to gases. But at room temperature and pressure, sugar and water are not gases, so you cannot apply that logic here, so this may not work. Take equal volumes of helium and carbon dioxide at this temperature and pressure. See, helium and carbon dioxide are both gases, and we treat all these gases as ideal gases, and they are both at the same temperature and they both have the same volume. Then they must have the same number of molecules according to Avogadro's law. Take equal masses of any two elements at the same temperature and pressure. No, this may not work. We have already tried that here. We took equal masses of oxygen and helium. They do not have equal number of moles. That means they do not have equal number of molecules. So this may not work. Take equal number of moles of any two substances. Of course, this would work. Right? 1 mole of any substance contains an Avogadro's constant of particles. So if you have equal number of moles, that means you have equal number of molecules.